Thank you. Thank you very much. It's a pleasure to be here. I'm sorry that it's virtual, but I guess we can still spend some time together, even if virtually. So as said, the title of the talk is Generalization in Deep Learning through the lens of implicit rank minimization. The content of this talk is based on 4 papers, starting from back in 2019 and until a very recent preprint. The first work was done at Princeton with Sanjeev Arora and students Wei Hu and Yuping Luo. And the latter 3 works are with my students Noam Lazin and Asaf Maman. So let's start by kind of setting the stage, just talking about implicit regularization and deep learning. So classically, generalization, in classical machine learning, we understand it through the bias-variance trade-off, which roughly speaking means that you want to learn a predictor that on one hand is rich enough, from a family that's rich enough to capture the relationships in your problem. On the other hand, you want it to be simple because you don't want to overfit. And so there's this kind of trade-off that you're trying to strike a balance with. You want a model that's simple, but not too simple. And controlling this trade-off can be done by limiting the size of your model, its capacity, or through regularization. For example, by adding an L2 penalty on the weights. This is our classical intuition, and it turns out that it doesn't really hold in deep learning. Empirically, in deep learning, we see that neural networks can generalize without any explicit regularization, despite the fact that in many settings, the number of learned parameters is far greater than the number of training examples. And the conventional wisdom around this is that the optimization algorithm, which is basically in one form or another, it's an algorithm that's based on gradient descent. This algorithm somehow induces some kind of implicit regularization that introduces a tendency towards simple solutions or solutions that generalize. And a major goal in the theory of deep learning is to mathematically characterize this phenomenon, to mathematically characterize the implicit regularization in deep learning. Okay, so we can appeal to a much simpler class of models, which is linear models. Think about linear regression. And it's known that in this case, when the number of weights is greater than the number of training examples, then running gradient descent initialized at 0 provably converges, leads to the minimum L2 norm solution. That means a solution that fits your training data. And from all the solutions that fit the training data, this one has the minimal Euclidean norm. And so this is a classic result. And it has led to a widespread hope by which something similar happens in deep learning. In deep learning, people hope that gradient descent somehow finds a solution that minimizes some kind of norm, not necessarily the Euclidean norm, not necessarily L2. So from all the solutions that fit the training data, somehow the optimization converges to one with minimal norm. And people have invested a lot of efforts in establishing such results in various settings. Okay, this is just a handful of papers, or a bit more than a handful from the last few years, but there are many more. And the perspective that I will try to convey today is that in order to understand implicit regularization in deep learning, the language of norm regularizers might not suffice. And actually, notions of rank may provide a better description of what's going on. And the models that I will use to try and make this case are matrix factorization and tensor factorizations, which are equivalent to certain types of neural networks. And so that's going to be the plan for today. And we will start with matrix factorization. So the setting that we look at here is matrix completion. In matrix completion, the objective is to recover an unknown matrix given a subset of its entries. We denote the observations by yij. I is the row index, j is the column index. And these indices range over some set of observed indices, omega. And you can think of this problem as a prediction problem. Specifically, it's a prediction problem with two inputs. Okay, so if I'm trying to complete a d by d prime matrix, I can look at this as a prediction problem where the input holds two integers, one between 1 and d, and the other between 1 and d prime. And the output is just a real scalar. Under this viewpoint, the value of entry ij in the matrix, that is the label of the input ij. The observed entries correspond to the training data, and the unobserved entries, they correspond to the test data. And a matrix, that's simply a predictor. And then if you have a matrix that agrees with the observations, that means that it is a predictor that agrees with the training data. And you are interested in to what extent it approximates the entries that you have not seen, meaning to what extent it is accurate on the test points. Okay. So matrix factorization, that corresponds to solving matrix completion by parameterizing the solution as a product of matrices. Okay, so I parameterize the matrix that I'm completing, that I'm kind of my solution. It's parameterized as a product, WL times WL minus 1, and so forth until W1. And the loss is just a summation over the observations, where I take my solution at the entry ij, and I take its square difference from the true observation at location ij. This is the model, and you just run gradient descent over this thing. Notice that you can restrict the rank of the solution by limiting these shared dimensions, but we are interested in the case where you do not do so. Okay, so in this case, the search space is unrestricted, and there's no explicit regularization. So matrix factorization can be seen as a linear neural network. It's a product of matrices. So it's a fully connected neural network with no nonlinear activations. That's called a linear neural network. And an empirical phenomenon, which at the time was surprising, was discovered by Gunnasecker et al. About 5 years ago, is that if you take this model and run gradient descent, starting from small initialization and with a small step size, oftentimes you will accurately recover the grand truth matrix if that has low rank. Okay, so if the grand truth has low rank, oftentimes matrix factorization will give you an accurate solution. And this is not a result of any explicit regularization. It is a result of implicit regularization. And we want to try and understand that. So let's talk about how this was viewed initially. So there's a classic result, which I'm sure many of you know. It's kind of a compressed sensing type result. And it states that if the grand truth is low rank and you have sufficiently many observations, then the solution that agrees with the observations and has minimal nuclear norm among the solutions that agree with the observations, the one that has minimal nuclear norm, that one will give you perfect recovery under certain decoherence technical conditions. And so this is a classic result. And a conjecture that Gunnasecker et al. Made was that under the hood, this is actually what's happening in matrix factorization. Meaning that when you train matrix factorization with small initialization and small step size, it essentially finds the minimal nuclear norm solution. So that was the conjecture at the time. Of course, if it were to be true, this would be very, very elegant. It means that the implicit regularization realizes some algorithm that has provable guarantees. And this was actually proven in certain restricted cases, both by Gunnasecker et al. And also by others later. So we approach this problem from a different angle, from a dynamical angle, analyzing the dynamics of gradient descent. And I'll kind of briefly discuss the results that we establish and then talk about their implications. So we take the product of all the matrices. We call this WE. E stands for end. This is the end matrix. It's basically kind of the effective mapping of the linear neural network. It's all the weight matrices multiplied by one another. And sigma MR, these are the singular values of the end matrix. So R is an index, and for different R's, you have different singular values. And what we can show in high level is the following. When I train a matrix factorization with small initialization and small step size, then the rate of evolution of these singular values is proportional to their size to the power of something. That something is 2 minus 2 over L. Recall that L is the number of layers. So if L equals 2, then this power is equal to 1. And the larger L is, the larger this power is. And so it means that the singular values, they move slowly when they are small. They move quickly when they are large. Okay? And so when you initialize close to 0, then you may expect that the singular values move very, very slowly. They barely move. And then trying to fit the loss one after the other, they will reach this critical threshold and start moving quickly until you get convergence. This is exactly what happens. Okay, this is a typical experiment. X-axis, that's the iterations of gradient descent. And you can see the singular values through time. And you see this incremental learning effect. And then you end up with a small set of singular values, which basically means that you get a low rank solution. This incremental learning process gives you a low rank solution. Okay? Now, going back to the question, to the conjecture, what we ask is it possible to characterize the implicit regularization as minimizing some kind of norm? So we have a dynamical characterization, but maybe it's also possible to characterize it as minimizing some norm. And it turns out that this is not the case, and you can show it with the dynamical characterization. You can show that there exist matrix completion settings where the implicit regularization of matrix factorization actually drives all the norms to infinity while minimizing the effective rank. And it's fairly easy to show this. I'm not going to get into proofs here. We can take it offline if anyone's interested. But the bottom line is that the implicit regularization in matrix factorization is not characterizable as minimization of a norm. And this also happens empirically. And this is kind of experimental data from one of these settings where this happens. And the lower the loss becomes, the higher the norms. And you get this result from the dynamical analysis. And so this is actually, as others have later developed these results and showed that it happens in various other settings. And now let's move on to talk about tensor factorization, aka CP factorization. Okay, so from a terminology standpoint, when I say tensor factorization, I mean CP factorization. So thus far, we looked at matrix factorization, and as a surrogate, as a theoretical model for deep learning, this is something that's fairly limited for two reasons. One is that it doesn't have any nonlinearity inside the network. And two, it only captures prediction with two input variables. When we viewed it as a prediction problem, we only had two input variables. And in order to address these limitations, we kind of lift matrices to tensors. Instead of thinking about matrix factorization, we think about tensor factorization. So now, the problem that we look at is tensor completion. And so a tensor, for our purposes, is just an n-dimensional array. N is called the order of the tensor. And we think about order n tensor completion, where you are given a subset of entries from an unknown order n tensor, and you're trying to complete the unobserved entries. And so the observations here, we denote them by y, I1 to In. Okay, I1 to In, these are the entries This is an entry that ranges over the set of observed entries. And extending the matrix case, you can think of an order n tensor completion problem as a prediction problem with n input variables, where input variable j ranges between 1 and dj. dj, that is the length of the j axis, or the dimension of mode j. Again, under this viewpoint, the value of an entry in a tensor, that's the label of the corresponding input. The entries that you observe, that is the training data. The entries that you do not observe, that's the test data. And a tensor is just a predictor. And so we can think of tensor completion as a prediction problem with multiple input variables. It also goes the other way around. If you have a prediction task, you can think about it as a tensor completion problem. Here's a super simple illustration. Suppose I'm just trying to classify images, and each image has 3 pixels. And every pixel can take one of 5 values. Kind of grayscale between white and black, and there are these 5 different values. So if these are my inputs, the tensor that corresponds to this is a tensor with order 3, because I have 3 pixels. And the dimension of each mode is 5, because every pixel can take on 5 values. And now every specific input, like this one, is mapped to a different location in the tensor. So where does this one map to? I look at the value in the first pixel. That's the first mode of the tensor. It tells me which coordinate, kind of where my location is along that axis. I do it with the other 2, and then that points to a certain location, and I store the label of that image inside this imaginary tensor. And I have many other images. I store them here. These are my training images. So I have the observed entries. And a test sample, that's an entry of the tensor that I have not seen. And so this is an image that I didn't have in the training set. And this is kind of how you can take a prediction problem and think about it as tensor completion. So tensor factorization, that corresponds to solving tensor completion by parameterizing the solution as a sum of outer products. Okay, so tensor factorization means CP factorization. It's just a sum of outer products. And then I fit the observations through gradient descent. So this is how my loss looks like. I sum over the observed entries. And for each one, I take that entry in my model, which is a sum of outer products. I take the square difference between that and the true observation. My model, the sum of outer products, has capital R summands. Each one of them is an outer product between n vectors, and we call it a component. So you have a sum of capital R components. Okay? So the tensor rank of a tensor, or the CP rank, that's the minimal number of components that are needed to express a tensor. And because we're interested in implicit regularization, we think about the case where the tensor rank is unconstrained, meaning that capital R is large enough to not constrain the rank of a tensor. Okay. And we're going to think about gradient descent over this model and talk about what kind of solutions it tends to find. I'll just note that just like matrix factorization corresponds to a linear neural network, tensor factorization can be shown to correspond to a nonlinear neural network. And specifically, it's a nonlinear convolutional neural network. More specifically, it's a shallow nonlinear convolutional neural network, so it only has one hidden layer. And so this is an equivalence that's actually been studied pretty extensively in the past 6-7 years, including by myself and colleagues, but it was studied, this equivalence, in the context of expressive power. So these models have not been studied in the context of implicit regularization much, and this is what we do. So we look at the dynamics of gradient descent over a tensor factorization. So now I take a component. This is the rth component. It's an outer product between these vectors. I take its Frobenius norm, and I denote it by sigma TR. Before we had sigma MR, that was M for matrix. Now it's sigma TR, T is for tensor. So sigma TR, that is the Frobenius norm of the rth component. And I think about how this thing evolves through time. Apparently, when I train tensor factorization with small initialization and small step size, the rate of evolution of these norms, these component norms, each one of them, each rate is proportional to the size of the component norm, or to the component norm to the power of something. And here this something is 2 minus 2 over n. So in the matrix case, we had 2 minus 2 over L, which was the number of layers. Here it's 2 minus 2 over n. N is the order of a tensor. So structurally, the dynamics are similar. And here too, that means that the component norms move slow when they are small, and they move fast when they are large. So if you initialize close to 0, you again expect component norms, they start off really small, they barely move. And then one after the other, they start crossing this critical threshold and moving quickly until you get convergence. And this is exactly what happens in practice. This is an experiment showing the iterations of gradient descent. And you can see the component norms. And there's this incremental effect where they kind of shoot up one by one. Ultimately, you get a solution with a small set of large components, which means low tensor rank. So this incremental learning of components leads to low tensor rank. And we can actually take this result and prove with it an end-to-end result that holds under certain technical conditions. We can show that if the tensor completion problem has a tensor rank 1 solution, then tensor factorization is guaranteed to reach it. Okay, so we could prove this using the dynamical analysis. Now, notice the kind of analogy between our findings. You have on the left matrix factorization and on the right tensor factorization. And so for matrix factorization, we talked about the singular values. For tensor factorization, we think about component norms. And each of them evolves at a rate that's proportional to its size to the power of, here it's 2 minus 2 over L, here it's 2 minus 2 over n. These dynamics lead to incremental learning. You could see it empirically here and here. This is for matrices, this is for tensors. In the matrix case, it leads to low rank. In the tensor case, it leads to low tensor rank. So the implicit regularizations here, from a dynamical perspective, in matrix and tensor factorization, they have kind of identical structure. Okay, let's now move to the kind of last model, which is another layer of complexity. So tensor factorization, that corresponds to a shallow nonlinear convolutional network. So it doesn't account for depth, which is an important part of deep learning. And to account for depth, we consider hierarchical tensor factorization. And kind of really roughly speaking, hierarchical tensor factorization forms a hierarchy of local tensor factorizations. So if each tensor factorization is a sum of components, in hierarchical tensor factorization, you have these local constructs, which are sums of local components. And it's known that just like tensor factorization corresponds to a shallow nonlinear net, tensor factorization corresponds to a deep nonlinear net. And this is something that's also known for quite a few years and has been studied extensively. One thing to note is that if I have a tensor and I can represent it with a hierarchical factorization that has a small number of local components in the different locations, that means that the tensor has low hierarchical tensor rank. Okay, so I'm presenting this relatively in high level and intuitively, but this is the gist of what a hierarchical tensor rank means. Okay. So what we now do, as we always, is look at the dynamics of gradient descent over this model. And here we think about local components. So sigma h, RH stands for hierarchical. That's the Frobenius norm of the rth local component in some location. And for that local component, we denote its order by k. And then we have this dynamical result that states that when you train a hierarchical tensor factorization with small initialization and step size, then these local component norms evolve at a rate that is proportional to their size, again, to the power of 2 minus 2 over k. Okay, so k here, that's the order of the local component. So again, these local component norms, they move slower when they are small, they move faster when they are large. And empirically, you get the exact same behavior. You initialize close to 0, they barely move. And then one by one, they start kind of incrementally rising. They cross this critical threshold and start moving quickly until convergence. And you get low hierarchical tensor rank solutions, okay? Just like before. Now, to kind of complete the picture, we can look at the case of matrix factorization, tensor factorization, and hierarchical tensor factorization, and you see that everything is structurally identical. In the matrix case, it's singular values. In the tensor case, it's component norms. In the hierarchical tensor case, it's local component norms. Each quantity evolves proportionally to itself, to the power of something. In the matrix case, it's 2 minus 2 over L. Tensor case, it's 2 minus 2 over N. Hierarchical tensor case, it's 2 minus 2 over K. L is the number of layers. N is the number of is the order of the tensor. K is the order of the local component. Empirically, you see that things behave kind of similarly. You have this incremental learning effect. And in the matrix case, it leads to low rank. Tensor case, it leads to low tensor rank. And in the hierarchical tensor case, it leads to low hierarchical tensor rank. What I want to talk about now is what this all means for modern deep learning. So besides kind of scientific curiosity, what does it actually mean? What can we do with these results? So this is kind of 3 implications that I'll talk about. One is a practical one. It's a practical application. And the technique here that this theory gives rise to is to just take layers of a neural network and parameterize them as a factorization. So if that layer, if it's a matrix, you can parameterize it as a matrix factorization. If it's a tensor, like in a convex 4-dimensional array, you can parameterize it as a tensor factorization or a hierarchical one. And then the implicit bias, the implicit regularization will minimize the rank. That means that your learned weights, they are compressible. So it can be used to improve computational efficiency at runtime, and it also can improve generalization. And this is something that's actually been applied in practice by various groups, including pure practitioners. This, for example, is a work by Jan LeCun's group in Facebook AI, and it's based on these theoretical results. Another application is more theoretical, and that's kind of a potential explanation for generalization on natural data, at least on certain natural data sets. So a challenge in explaining implicit regularization is that we're looking for complexity measures that, on one hand, are implicitly minimized when you run gradient descent over neural nets. And on the other hand, they capture the essence of natural data in the sense that you could actually fit natural data with low complexity. And then that would complete an explanation for generalization, because you're training your model. It has a bias towards the lowest complexity solution. And you know that you can fit the data with low complexity solutions. So you will get a low complexity solution, and then you can guarantee generalization. This is something that a lot of people are trying to achieve. And the question we ask, given that gradient descent over the neural nets that we looked at minimizes ranks, the question we ask is whether ranks can capture the essence of natural data. Can they serve as measures of complexity? And to that end, we run an experiment. I won't get into the details too much. Just say that what we show is that simple data sets like MNIST or fashion MNIST, we show that they can be fit with predictors of super low rank. Okay, so a predictor, you can think about it as a tensor, and the tensors corresponding to these predictors could have very, very low rank. You can still fit the data perfectly. Okay, so at least for these data sets, we can actually get an explanation of why the neural networks that we looked at, why they generalize. Okay. The last implication is kind of, again, more practical. Here we look at the some new regularization technique for convolutional networks. So a well-known fact is that hierarchical tensor rank for a tensor that quantifies the long-range dependencies of the predictor that corresponds to the tensor. Long-range dependencies, that means dependencies between areas that are far apart in the input. Like if the input is an image or if it's a text sequence, then between elements of the input that are far apart. This means that what we've seen, the implicit minimization of hierarchical tensor rank in a hierarchical tensor factorization, from the viewpoint of CNNs, convolutional nets, that means that there's an implicit minimization of long-range dependencies. So it's known that convolutional networks, empirically, it's known that they're not great for tasks that have long-range dependencies. This is something that's known. And the conventional wisdom is that this is because of their architecture. Because their architecture has these local operations, then the models are not even able to express functions that have long-range dependencies. What our results imply is that it's not just about the architecture, it's not just about expressiveness, it's also a result of an implicit regularization. There's also an implicit regularization that pushes towards local dependencies. And this kind of raises the question of whether it is possible to design explicit regularization that will counter this implicit regularization, thereby improving CNNs on tasks with long-range dependencies. So it's important. If the poor performance on long-range tasks results from expressiveness, you can't do anything besides change the architecture. On the other hand, if it's a result of implicit regularization, then you can try and intervene through some explicit regularization and improve the situation. And this is what we try to do. So we take two data sets. One is, both are synthetic. One is one that we designed, the other is standard. So the first on the left, it's called we call it is same class. It means that you get as inputs this kind of stripe, and it includes two CFAR10 images, and you're supposed to say if it's the same class or not. So here it's two cars, it's a positive example. Here it's a plane and a dog, it's not. So this is a negative example. And you have different data sets for this task. And you have a data set with zero distance between the cars. So all the or between the images. So every pair of images you get, they are adjacent to one another. So this is a task that doesn't have very long range dependencies. On the other hand, on the bottom, this is a task where the images have a big gap between them, like 160 pixels. So here, to solve this problem, the model needs to model long-range dependencies. The network, the neural network needs to model long-range dependencies. So that's one data set. The other is called Pathfinder. And for Pathfinder, you have these dashed curves, and you're supposed to say if the white circles reside on the same curve or not. So this is a positive example. This is a negative. And for each task, you have multiple data sets. They differ in the length of the connecting curve. So this is a curve of length 6, and this is a data set with curves of length 9. So the longer the curves, the longer the range of dependencies you need to model. And so these are the data sets. And you can see the performance of a standard convet, ResNet 18. You can see the performance as we move to a data set that has longer range dependencies. So for the data set for is same class, the distance between the two images gets larger. The performance of the convet drops until it reaches something that's close to chance, 50%. In the Pathfinder, you can also see that it goes down, again, until reaching something close to performance of chance. And what we do to try to improve the situation is introduce regularization. And specifically, we introduce regularization that promotes high hierarchical tensor rank, which means long range dependencies. And the same model, the exact same model with this regularization performs much better on the tasks with long range dependencies. So it almost closes the gap. The blue is with regularization, the red is without. This 50% line, that's trivial performance. So going down from here, from here to here, that means basically going from something that captures some of the problem to nothing at all. And the blue almost recovers the performance that you had with short range. The bottom line is that through explicit regularization, you can indeed improve convolutional networks on long-range tests. And this is something that's not it's pretty surprising. It doesn't go along with the conventional wisdom by which you have to change the architecture. That's what I used to think. So this was surprising to me as well. All right, so let's conclude. We'll have some time for questions. So starting with a short recap. So a goal that we set out to try and make progress on is understanding the implicit regularization in deep learning. We looked at 3 models, starting with matrix factorization, which corresponds to linear neural networks. There's an existing conjecture there that the implicit regularization minimizes the norm. And we have seen dynamically that it gives rise to a process that minimizes rank and that can actually drive all norms to infinity. When looking at tensor and hierarchical tensor factorizations, which correspond to shallow and deep nonlinear nets, nonlinear convolutional nets, we showed through dynamical analyses that the implicit regularizations minimize tensorial ranks, CP rank and hierarchical rank. And this led to several implications for practical deep learning. One was to parameterize layers of a neural network as a matrix or tensor or hierarchical tensor factorization that gives you compression, something that many people did. Another is that rank minimization, at least for simple data sets, it can explain why the neural networks that we analyzed, why they generalize. And finally, we show that one can encounter the one can counter the locality of CNNs using explicit regularization without changing the architecture at all. I'll just close off by saying that we've seen that different types of neural networks, whether it be linear or certain nonlinear models, each of them minimizes some different notion of rank. It could be matrix rank in the linear neural network case, or tensor rank in this shallow model case, or hierarchical tensor rank in this deep model case. So every architecture has its own notion of rank. And I believe that maybe this applies to state-of-the-art architectures as well, like dense nets or attention models. In each architecture, when you run gradient descent, you implicitly minimize some corresponding notion of rank. And if this is true and we are able to discover the minimized notions of rank, then that could help us both have a better understanding of generalization for the analyzed architectures and also maybe improve their performance. by introducing new regularization schemes, like we did based on the analysis here, introducing high hierarchical tensor rings. Or maybe you can modify the architecture so that it'll change the notion of rank that's being minimized to something that's more suitable for your problem. So the bottom line is that I think that in a generalized sense, rank, the concept of rank, might really be helpful in deepening our understanding of deep learning. And with that, I think I'll close. Thanks everyone for your attention.